So I want to move on to a little bit more practical view of doing MEG recordings using OPMs. And the outline of my talk is that I'm going to talk about sources of noise in EG. Like people that are new to MEG might have familiarity with EG. So that's also something that I want to highlight. And of course, but I'll also be comparing SQUID MEG and OPM MEG. And how do we deal with noise in hardware and during offline processing? And an important thing to discuss is that we still have to figure out procedures for OPMs, whereas we already have those procedures as of 20 years for the SQUID hardware. So I'm going to discuss some of the differences that we have. Then I'll touch upon data formats, like how do we represent the data on disk, and how do we get the data into our analysis software, and how do we process our analysis, our OPM data in the analysis software. Because the advantage of OPMs over SQUIDs is that OPMs don't need cryo cooling. Each sensor has its own its own housing, which allows for flexible placement. It's relatively lightweight, allows OPM measurements during moving. And as such, I would say that OPMs combine the advantages that MEG has, a high spatial resolution, with the advantage that EG has, which is like very wearable and lightweight and very comfortable for the participant if you exclude the preparation time, which is a little bit annoying with the EG. Looking at EG, there's a large number of sources of noise that we can identify, and then a very important category of noise is the physiological noise. Muscle activity, eye activity also produces electric fields. We have brain sources that are not of interest. We have eye movements, we have muscle activity, including the regular beating of the heart. But there's also physiological activity such as sweating, which causes the electrolyte layer between the electrode and the brain to change. So that also causes signals that we're not interested in. There's behavioral noise, such as the participant moving, especially abrupt movements, which cause the electrodes to shift a little bit relative to the scalp. There's environmental noise from equipment, electrostatic noise, which is often very prominent at the line noise frequencies at 50 or at 60 hertz. And there can be radio frequency noise, for example, if you have a cell phone nearby. There's also noise that is due to the instrumentation itself, so not noise necessarily due to the interface with the participant or due to the participant, but there can also be limitations in the hardware, such as the saturation of the amplifier and clipping of the signals, or large common mode signals between the electrode of interest and the reference electrodes, which causes, if the common mode rejection ratio is not so large, which causes artifacts that are also visible. If we compare these EG sources of noise to MEG sources of noise, then you see that a lot of the sources of noise are actually the same. So the physiological sources of noise, they remain the same, because whenever you have an electric current, you also have a magnetic field. So of all of these bioelectric phenomena, they produce magnetic signals. The behavioral noise, however, is a little bit different. One of the sources of noise in MEG is, for example, wearing jeans and then breathing, and then the rivets on your jeans moving along with the breathing, which causes magnetic fields to change. There's environmental noise, which is different from the MEG, because there can be magnetic noise sources relatively far away from your recording setup, such as cables going into your magnetically shielded room, but also nearby elevator or cars driving by. And SQUID MEG measurements are done in a magnetically shielded room. It's the room itself that can vibrate a little bit. And this is something that actually until recently I was not so much aware of, but these rooms are not as robust as we think. And depending on the construction of the room, the vibrations of the room cause vibrations to be visible in the MEG signal. With SQUID MEG recordings, there's also some instrumentation challenges. So we have nonlinear transducers. So SQUIDs operate also with a closed loop feedback to try to make it very linear, and actually it's very linear over a very wide range. But with SQUID sensors, we also occasionally have a quantum flux jump or a SQUID jump, as we call them. Moving on to OPM MEG recordings. So again, transition. There's actually not that much difference between the type of noise artifacts that we have with SQUID MEG and with OPM MEG. So the physiological noise is the same. The behavioral noise, the participant wearing something metallic that moves, is the same. But now one of the additional sources of noise is that the OPMs can move in the residual Earth magnetic field. And that's, of course, a great advantage of OPM, but it's, of course, also something that we have to deal with. The nonlinearity of the transducer, so the sensors that translate the magnetic field into something that is stored on the computer, is actually a little bit more challenging with OPMs than it is with SQUID. And it's also the presence of large fields, or relatively large fields, like more than, let's say, a 10 nanotesla or so, which can cause artifacts with the OPMs that we're not so much used to seeing with the SQUIDs, because the sensors can unlock and can basically behave unexpectedly. So if we look at EEG, and if you then ask the question, how is noise dealt with in the case of EEG? The primary strategy that we use is that we try to prevent it during the recording. And I will explain a little bit in a coming slide how we prevent it during the recording. But if noise cannot be prevented, then it's in the analysis that we deal with it. We often have short-lived transient bursts of noise, for example, an eye blink. And if we then do an experiment, for example, an experimental design with 100 trials, you can cut the data into segments, you would analyze those segments, and you can reject those segments that have a large burst of noise. So this is a very common strategy, just rejecting trials that are noisy. There's also artifacts that are continuously present, which cannot be rejected that way, as that would remove all the data. And in those cases, we try to remove it or try to subtract it from the data. So this has been done for ages. So linear regression for ocular artifacts was already done in the 80s. Principal component analysis kind of used. Independent component analysis, a very popular and very widely used technique for reducing the artifacts in EEG. Preventing noise during the recording, in the case of EEG, is done by a smart choice of the electrode material. We typically use silver chloride electrodes and a matching electrolyte gel to make the recording stable. We have a very smart EEG amplifier designs, including a reference and a ground electrode, or a driven right leg and a common sense. There's standard procedures that you might not think about, but for example, where do you place the reference, where do you place the ground electrodes, that all influences the amount of artifacts that you can record. We prepare the skin, we try to get the impedance down, we try to use short cables, we can use active electrodes. So these are all aspects that relate to the part that is close to the head. But we're also doing efforts in the lab setup. For example, we make the whole lab into a Faraday cage, which reduces the environmental fields. And that's also useful for acoustic shielding. So the participant will behave better if the participant is not being disturbed by people talking in the hallway, for example. There's other things, such as the lighting that you have in the ceiling of your lab, that's going to influence the amount of noise that you're going to pick up. So we don't use fluorescent tubes, we would rather use LEDs or tungsten lighting. And again, to prevent artifacts from happening, good instructions to the participants are really useful. So very often we'll have experimental designs in which we tell the participant when to blink, because then we can prevent the blinking during the presentation of the stimulus. It would actually have the blink in between of two trials where it actually doesn't interfere with our data collection. Or we give the participants explicit breaks in which the participant can move, relax a little bit, and those type of things, so that during the experimental runs of interest, that the participant is more relaxed and that we don't have the muscle activity of the participant sitting uncomfortably. With the EEG, it's also very important that we have offline data cleaning. So common to both ocular regression, PCA, and ICA type of method is the concept of spatial temporal mixing of the brain signals of interest with noise sources. These noise sources are usually assumed to be stationary, so their topography remains the same, and it's only the amplitude of the noise that varies. And sometimes the amplitude can be 0 when it's absent, but basically we're assuming that these noise sources always have the same topography. And except for electrode movements that are relative to the scalp, which are really nasty artifacts, so there's some interesting methods for that as well, as recently presented by Norden et al. The EEG signal and many noise signals don't change with small head movements. So from a mathematical perspective, we say that the data matrix Y is a linear mixture of a gain matrix times the sources X, And if we consider the sources as separate components, we can unmix the data as we're doing with ICA, and we can identify some of the sources that contribute to the signal as noise sources, and we can basically reconstruct the data without those noise sources present. In the case of MEG, we prevent noise first and foremost by having a passive shielding of the room with the layers of new metal and aluminium. And on top of that, we can use active shielding with coils. And these coils can be driven with a constant current, creating a DC field, or these coils can be driven with a current that actually changes over time, whereby you can also compensate for the magnetic fields changing over the course of time. Of course, we're very used to having smart design of the MEG sensors in electronics, for example, using radiometers and using closed loop operation. And again, we not only have to think about the characteristics of the recording equipment and of the room, but also of the participants. So in MEG or SQUID MEG measurements, it's very important that we prevent the participant from moving. So making sure that there's comfortable seating, putting some cushions around the neck or around the head, for example, to keep the head fixed or to keep the head stable in the helmet. It doesn't have to be fixed, but it has to be stable so that the participant can sit relaxed. Some labs use the degaussing systems to actually remove the magnetic field from small magnetic particles that can be present in the participant or like the dental wires. We usually ask participants to not wear jeans. We have them change to other clothes. No underwire bras, no magnetic metals basically on the body, and also no magnetic metal or no electric currents enclosed by stimulus equipment. So button boxes, which for EG can simply be keyboards. In the MEG lab, we use button boxes that comprise of a laser beam, which is interrupted by the participant pressing a button. So there's no metal in there and there's no electric currents in there. The magnetically shielded room, as shown here, basically has the function to absorb the magnetic field of the environmental field. So it's both the Earth magnetic field, but it's also a magnetic field of things that are changing in the environment, such as an elevator or a trolley driving by in a corridor, are absorbed by the wall, and it's the center of the magnetically shielded room where the magnetic fields are the smallest. This is important to know because it's also the center where we place the CTF system, or sorry, the SQUID-based MEG system. But it's also the center of the room, which would be the best for OPM measurements, because that's where the gradients, that's where the field is the smallest, but that's also where the gradients are the smallest. And I think an interesting characteristic is going to be to see how, if we decrease the size of the shields for OPM recordings with a tubular shield or with person-size shields, is how these gradients, which are like large to the walls, are they still going to affect the measurements? I think that's still something that I look forward to other people presenting. The initial magnetically shielded room, or actually the optimal design of a magnetically shielded room, would be a sphere. So the initial magnetically shielded room that was designed by Cohen and colleagues at MIT was pretty spherical. But of course, such a room takes a lot of space. So nowadays, we don't use these spherical rooms anymore, but we've converged to these like more cubic rooms, where the size of the room is largely dictated by the size of the CTF viewer, the MEG, the SQUID-based MEG viewer. It has to fill in, which is relatively tall because you need to fill it from the top with helium. So we're now used to having quite large magnetically shielded rooms. Of course, for behavioral experiments, for EEG experiments, we don't necessarily need such large rooms. I think that's an interesting opportunity that we have. On top of the magnetic shielded room with the mu metal walls, we can add active shielding with noise cancellation coils, with which we create magnetic fields that are opposite to the fields that's from the environment. This has been used for a long time in SQUID-based MEG measurements, and of course it's again important to consider this for OPM measurements. And a very important step is that we have smart sensor designs. So with a SQUID-based MEG system, we have the SQUID itself, but we're not necessarily only restricting ourselves to the SQUID. So every SQUID has an IOBM antenna attached to it, or a pickup coil, with which we can amplify the fields, and with which we can make more flexible arrangements of the sensors. So what you see here is the antenna that will be connected here at the top to the SQUID. for a magnetometer. So it's a single coil, and the field goes through such a single coil, and that's basically what we would be interested in. But at the same time, we would also have environmental magnetic fields going through it, so the environmental noise, which would be picked up just in the same way as we would with the pick up the brain activity. If we then consider an actual gradiometer, then we're extending the antenna with a second coil that is of an opposite direction. So the consequence of this is that the brain activity is picked up stronger in the coil that is closer to the brain and weaker in the coil that is further away from the brain. And since we're looking at the difference, we record it as a gradient. But the environmental field, which is from a faraway source, is actually the same at the top coil and at the bottom coil, so that would be very efficiently cancelled out. So a gradiometer has a very good property of suppressing environmental noise while still picking up activity from the brain. So these were the type of sensors that were first designed with one coil close to the brain, one coil further away. But then, of course, Neuromag came up with the idea of using planar gradiometers, where actually the two coils are in the same plane, and where the gradient is not measured in this direction, but where it's measured in this direction. The principle here is the same. So the two coils pick up the activity from the brain, which is differential on the two sides of the dipolar pattern, and the environmental noise is the same on both sides of the coils, and is very efficiently suppressed. So looking at reference sensors and synthetic radiometers, so with the SQUID, we have these superconductive pickup antennas, and then we can make sensors such that they consist of multiple coils. And since superconductivity really has no resistance at all, these superconductive coils, they have perfect noise-free subtraction between the two coils. And it's perfect to the sense that these coils have exactly the same size, and with the planar gradients with the planar gradiometers from Neuromag, with this thin film technology, these coils can be very accurately calibrated, so the suppression is really very good. But the disadvantage is that these are fixed in their design. So rather than building a hardware gradiometer with the antenna design, you can also take a sensor that's close to the head and use that to subtract the signal from the reference sensor, and use that, and then subtract the signal from a reference sensor that's further away from the head. And that is a technique that is used both by CTF and by BTI or 4D neuroimaging. So they have a sensor array which is like head-shaped in the helmet close by, and they have additional sensors that are slightly further away. BTI has magnetometers, the CTF system has gradiometers, but the principle basically applies to both. You just measure the gradient of the noise far away from the head, and you subtract it from the signal that you're recording close to the head. For the CTF system, we can make use of a mathematical model of the first, the second, and the third order spatial gradients using these reference sensors, and use that to remove the estimated environmental noise and their spatial gradients. In the BTI system, the reference sensors are used to compute the correlation of their signal with that on the MEG sensors, which is done in a calibration session without the participant being in there. So it's in an empty room recording. And in a way that is then more similar to the Graton eye correction algorithm or to signal space projection type of methods. So reference sensors are really nice, but there's also some challenges with them. And if you have a few reference sensors, and if you subtract a linearly weighted combination of their signal from the MEG signal, then you're also subtracting or adding the noise of those reference sensors. So noisy references means that the signal that you're getting will also have increased noise. So if you consider one sensor of interest that is close to the brain and one sensor that is further away, then the sensor noise, so the noise that is really intrinsic to the sensor, is going to be independent. And the noise that you're going to get by subtracting the two is going to increase with a factor of square root of 2, which is about 40% increase. So that is well understood. It's one of the reasons that with OPMs already being slightly more noisy than SQUIDs, the prospect of building an OPM gradiometer using two independent OPM sensors is not that attractive, because it will just increase the noise even further. So that's why people are working on making OPM gradiometers in hardware rather than doing them synthetically in software. Another solution that is actually widely used is not not to use a few sensors for the reference subtraction, but use all the channels that you have to estimate the noise and to subtract that. The advantage of that is that the noise averages out between all the sensors that you're including to estimate the noise. And this is actually more similar to PCA and ICA in EEG. And this is also what is used by, which is used by the NeuroMag or Electro or MEG system if you're doing SSS. So some of the methods that use this idea of like using all the channels to estimate the noise and subtract it from the data are signal space projection, dual signal space projection, signal space separation, and temporal signal space separation. And there's other methods like this, but all of these methods basically share this idea of using all the sensors to capture the noise, to model the noise, and to subtract it. One of these noise sources that is really unique with OPMs compared to squid-based MEG measurements is that due to head movements. And that's just something that I want to explain a little bit more explicitly. So if you imagine that you have this residual field and you have this sensor that is picking up the field in this direction of the residual field, and if the sensor is attached to the head and the subject makes a 90-degree rotation, the sensor would also rotate 90 degrees. And all of a sudden, it's the environmental field that becomes your signal. So if you have a residual field in your MSR of, let's say, 5 nanotesla, and if you rotate your sensor by 90 degrees, you're going to see 5 nanotesla, you're going to see 0. And since we're interested like in pico and femtotesla fields, a 5 nanotesla artifact is really big. For the same argument holds if you consider the spatial gradients that we have in the magnetic shielded room. So if you move a sensor in one direction, and if the field lines diverge in that direction, the field can go from larger to smaller. So it's also the residual spatial gradients in the magnetically shielded room that interfere with head movements and with head rotations. So thinking on how to deal with head movements and OPMs, one of the strategies that we can use is to make the overall residual background fields as small as possible using the MSR. So we can add additional layers of mu metal, which is possible but also expensive and heavy. And we can use Helmholtz coils. But since we're also sensitive to the residual gradients, we also have to make these residual background gradients as small as possible. And that's where additional layers of mu metal help. But it also needs more complex coil configurations, like the planar gradient coils and matrix coils. Coils outside of the magnetically shielded room, which can help to reduce the Earth magnetic field, they don't help to reduce these gradients. The gradients are largely introduced by the MSR. It's the walls of the MSR that basically curve the field. But coils inside the magnetically shielded room, they can reduce the gradients. So this is not something that is new. This is also something that we've been using for squid MEG. So many of the NeuroMag Electro MEG systems have used both internal and external coils and use internal active shielding to reduce the noise in the recording. So at the Donders, we've been for about 1 year, we've been experimenting with OPM. So we have a 32-channel OPM system. And initially, when we set it up, we started by adding simple Helmholtz-style coils inside our magnetically shielded room. So here you can see them. Here you can see them like along the wall. There's basically like a blue wire running over the wall. That's this wire. And here on the front wall and on the floor, we have similar coils. And with these very simple with these very simple coils, we were able to reduce the magnetic field quite a bit. Just in case, we're actually at this moment we're not using them anymore, because when the sensors arrived, so this is something that we installed prior to the OPM sensors arriving. When the OPM sensors arrived, it turned out that their operating range was so large that actually the residual field in our MSR was not a problem. This is also a design that you've already seen, like it's more of a box-shaped arrangement of Helmholtz coils that was developed at Aalto, that was tried out there. It's not as friendly for the participant because the participant has to slide in the box, has to stick his head in. It's rather present. So that's why people moved on with this and came up with the idea of planar nulling coils. So here you can see me sitting in the OPM system at the Karolinska Institute in Stockholm with two relatively small planar gradient coils along the sides to remove the environmental field. The next step that people are now taking, that researchers are now taking, especially in Nottingham, is the design of matrix coils. So coming up with even more elaborate configurations of coils on the walls, but also on all the walls, and also on the ceiling and on the floor of the magnetic shield room, with which the gradients, the residual field and the gradients in the magnetic shield room can be further suppressed to create a noise-free environment where the OPMs work well, but also where head movements do not cause large artifacts. Just to give you an idea on how these gradients look like, these are recordings that were done in the magnetically shielded room at the Donders in Nijmegen, and this is after first order homogeneous field correction. So the Earth magnetic field, so it's basically the homogeneous component of the magnetic field has been removed. And what you see here is like in the referenced fields that are in the order of like 10 nanotesla, and it's in the middle of the room where the head is. So this is more or less where the chair is. This is more or less where the head is. The residual fields that we would get if we would have perfect homogeneous field compensation would be in the order of magnitude of 5 nanotesla. What you also see is that if you move further away from the center of the room where the residual fields are the smallest, the gradients actually cause the fields to increase. And especially here, if we get closer to the floor, the field actually increases quite a bit and becomes very steep. Here is the side view, and you see the same thing from the top. Of course, here, this is basically, the gradients are large for the points close to the floor. So this is not necessarily a problem for the area in which we expect our participants head to be, because we're mainly doing head fixed recordings with the head in the middle of the room. Moving on from trying to avoid noise in the recording to dealing with noise that was recorded and offline data cleaning. The general model of spatial temporal mixing of many brain and environmental sources into the noisy MEG signal is basically, it's the same as what we already know from EEG. And as such, all the methods that we can use for EEG can also be used for MEG. So PCA, ICA, and those things can also be used. However, compared to EEG, in MEG, we often make more explicit physical and biophysical models for the sources from the brain and for the sources from the environment. And that's really a very important difference in the techniques that are used for EEG versus the techniques for MEG. And it's because the forward model for MEG is better understood than for EEG, and it's simpler. So again, thinking of this data being a spatial temporal mixing of the signals of interest X times a gain matrix, with MEG and with forward models, we can make a better distinction between sources that are of interest, for example, of this inner sphere, as Samu showed you for using SSS, and this external environment where you would have noise sources that you can suppress. And using techniques such as SSS, we separate the sources from the compartment of interest, the head, from those from the compartment of no interest, which is the outside world. So besides SSB, dual space SSB, SSS, TSSS, which we use, which are very common for squid-based MEG. For OPM MEG, there's new techniques being developed, such as homogeneous field correction, HFC, and adaptive multiple modeling, AMM. Besides doing channel level cleaning, it's also important to consider that since MEG has a very high spatial resolution, we're often doing recordings to reconstruct activity on the cortical level. And we can reduce the impact of the noise during the source reconstruction. And beamforming is one of these techniques that explicitly makes a separation between the signal of interest from a region of interest and the noise. So beamforming adapts to the noise present in the data. The noise is not modeled explicitly, but it's assumed to be represented in the data covariance matrix. And this data covariance matrix is a mixture of the source of interest and the noise, which is basically everything else. The source of interest is explicitly modeled as a dipole, and its strength is estimated using a unit gain spatial passband filter, and everything else is being suppressed to the maximum extent possible using a minimum variance output. And this leads to beamforming implementations such as LCMV, DICS, SAM, and others. So I think still interesting to see is like how much do we have to suppress the noise on the channel level, or how much can we rely on source level reconstruction also dealing with the noise. With the CTF system that we have in Nijmegen, Actually, we're not using third order gradients because we're using beamforming a lot, and beamforming deals with the noise just as efficiently as the channel level cleaning would. With OPM, we have head movement, and in squid-based systems, the head is not fixed to the helmet, and movement of the head causes inside the helmet causes blurring of the average brain activity over trials. However, OPM systems can be designed such that the sensors do not move relative to the head, but move along with the head. And that's where some also already mentioned. We have, on one hand, we can say, well, the head moves together with the sensors in the residual environmental field, which is fixed in space. But from the data cleaning perspective, we can also say it's the space that moves around the head. So if we see everything from the head-based coordinate system, it's the noise sources that move around the participant rather than the participant moving with its noise sources. And of course, that makes certain types of cleaning procedures much simpler for MEG if we just basically say, well, we have two coordinate frames in which we can represent this. If the head and the OPM sensors are moving slightly independently from each other, so if you imagine an OPM helmet that wobbles on the head if the participant is moving the head, then the spatial temporal mixing becomes and hence also the cleaning becomes quite a bit more complex. So the OPMs being fixed to the head, I think, is an important requirement or for data cleaning to be efficient. So it's just something to consider if you're designing your own helmet. Then moving on more to the data analysis, to co-registration, to source reconstruction. Squid-based MEG systems have all well-established software and standard procedures, and they all work with head position indicator coils, which are placed on anatomical landmarks, usually the ears and on the nose. And the acquisition software does the co-registration and stores the MEG sensors relative to the anatomical landmarks. On top of that, we can use polyimous electromagnetic digitization systems, which are common, and they allow us to record the HPI coils relative to these landmarks if you place them somewhere else. But we can also use the polyimers to record head shape. And the head shape is then used during the offline co-registration, because that's where we take the individual subject's MRI, we take the MEG sensor positions, where we move them such that the MRI and sensor positions that they match. So this is done using anatomical landmarks, and this can optionally also be done using these additional head shape points that we record with the polymers. In OPM systems and in OPM software, these procedures are still less complete. Given the flexibility that we have with OPM systems, there's also not really one standard that all the systems are using. OPMs allow for flexible placements, custom 3D printed helmets and caps. And in that case, also the acquisition software actually doesn't even know the position of its sensors to start with. And it's important to realize that not only the OPM position needs to be determined, but also its orientation in space, so it's multiple axes. OPM co-registration can use the same principles as that for squid, so we can use HPI coils that are sequentially simultaneously activated at the start of a session. The polyimers electromagnetic digitizer can be used to co-register the helmet with points on the head. A technique that we use at the Donders in Nijmegen is 3D photogrammetry. So we take a 3D scan of the face of the participant together with the front part of the helmet. And the Fieldline Smart helmet localizes the OPM sensors that are touching the scalp, and as such, it not only gives the position of the sensor, but also gives an estimate of the head surface, which can also be used for co-registration purposes. If you consider OPMs in a fixed or in a rigid helmet, you can localize them as an array. So if all the sensor positions are known relative to each other, it's just all the sensors that are moving along with each other. Whereas if you have an individual EEG style cap which stretches and where the sensors can also tilt a little bit, then you have to start thinking about localizing and determining the position of each individual sensor separately. The MAG for Health system has a little bit of an in-between solution where they have a cap with flexible material with larger arrays of sensors. So there's multiple sensors on each panel. There's multiple arrays. So that's a little bit in between. So each of the panels can be individually can be localized, but the panels differently also have to be individually localized. Again, moving further towards the analysis. So OPM data, of course, gets stored on a computer, and we need to read it in our analysis software. And most SQUID-based MEG systems have their own format. And since we are so common to them, those formats are well supported in all the toolboxes. The fifth file format was developed in the 2000s for the NURMAG system, and is very flexible in using tags, just like the TIFF or the AVI or the DICOM format. And that's a well-supported format for Python, MATLAB, and C++, both for reading and writing. And although it's not a perfect format, I consider it the best format that we have right now in moving forward with OPM system development. So I'm hoping that OPM vendors are going to adopt the fifth format because we already have the support for it. The fifth format we already know for a long time. It not only works for NeuroMag data, it also allows for representing data from other SQUID-based MEG systems such as CTF and BTI. And it has a very the fifth format allows for a very detailed description of the sensor, so the spatial extent of the sensors, and for OPMs we also allow for modeling the spatial volume of the sensors in a separate coil definition file. But considering the files that we have from SQUID-based MEG recordings, and that the same thing will hold for OPM-based recordings, in general, the raw data files do not contain all the experimental details. For example, what was the task? What do the trigger codes mean? What are the auxiliary channels containing? How was co-registration on? There's a lot of information in the experimental procedure that is not stored in the binary file. And that's where BITS comes in. BITS is a project that started in 2016, more or less. It's the brain imaging data structure. And it's a way of organizing your existing raw data to improve consistency and complete documentation, and to facilitate reuse by yourself and by others. So BITS is not a new file format, or it's not a data search engine or a data sharing platform, but BITS is a strategy to add missing bits to the data. And considering FAIR principles, BITS aims to improve the interoperability and reusability of data sets. So I just want to give you an example of a BITS data set. So this is a directory structure that you would have. And over here, you see the actual MEG signals stored in a FIF file. On top of that, BITS comes with a prescribed directory structure where the anatomical MRI of a participant also has a clear place, where additional EEG recordings would also have their additional place. And BITS comes with quite a bit of metadata that describes those parts of the experiment that otherwise would not be known. And I also do hope that MEG vendors are going to adopt BITS, or especially OPM vendors who are still developing the software are going to adopt BITS to add all of these missing bits to the recording on disk, because that greatly facilitates the processing and sharing of data. BITS is supported by many software packages like Fieldtrip, M&E, Python, SPM, Brainstorm, and others. And it's also the de facto standard for the Open Neuro and the public Neuro repositories, and for platforms such as BrainLife. BITS is a standard. BITS is being extended all the time. So we're with different extension proposals, new modalities are being added to BITS. But the fifth file format already is allowed with the BITS standard. Other file formats could be added to BITS, but at this moment they're not part of the BITS standard. So that's why I'm encouraging people to work with the fifth file format. The parts that still need to be added, for which we don't have the standard procedures yet, are the metadata description of the co-registration procedure, because we have multiple co-registration procedures. The details of the OPM sensors, because OPM sensors are more variable between vendors. And the details on the OPM helmets or caps and the placement system need to also be added. And this is where there's definitely work to be done in the BITS community together with the MEG community to improve the documentation of the data. And once you have the data well annotated with additional information in the BITS file format, and once the OPM signals, the triggers, and the events are known, sensor positions are known, co-registration is done, then processing is actually business as usual. And it's mostly similar to SQUID-based MEG. Event-related fields, power spectra, time frequency analysis all work the same as with SQUID-based MEG. There's some signal characteristics that are different, such as bandwidth and tangential sensitivity, but that's not tremendously different. And it's also important to realize that forward models are not different between OPM MEG and SQUID-based MEG. So all of the techniques that have already been implemented can simply be used for OPM MEG. And also inverse methods are not different between OPM MEG, SQUID MEG. Actually, they're also not different than EG. OPM MEG processing is different to SQUID MEG in some regards, so the data cleaning procedures are slightly different. Dealing with participant movement during the experiment is definitely a new challenge. But there's also plotting of spatial topographies. That is not so trivial if you have biaxial or triaxial system, because all of a sudden we don't have scalar values anymore, but we have vector-based values. So standard template layouts for plotting do not apply to custom 3D printed helmets. This is a little bit a situation that we already know for the Neuromac planar system, but that's something that we definitely can solve. So existing open source MEG analysis toolboxes can read the data, and they already all have support for OPMs. And with the respective projects, we are working on adding further OPM specific functionality, documentation, and tutorials. So I'm the main developer of FieldTrip, which has very good OPM support. It's something that we're using. We have OPM tutorials already on the website, but I know that also the M&E, the SPM, and the Brainstorm teams have OPM support, have OPM documentation, and I really encourage you to adopt those toolboxes rather than to try to develop your own toolbox from scratch, because there's just so much overlap between SQUID-based and OPM-based MEG. Also, existing guidelines, for example, the guidelines from Joachim Gross and teaching material also apply to OPMs, and there's excellent books for OPM, for MEG recordings that also apply to OPMs. So I really encourage you to take the knowledge from SQUID-based MEG and start using that for OPM-based MEG. That's what I had to say. Thank you.